Hello learners, welcome to Education Online program. I am teacher Willa Lucia. Today we shall be learning about the application of the principle of moments. Application of the principle of moments. So we are going to start with the first application, which is the parallel forces. Let me have it there as our parallel force, or you can say forces when there are many. What are these parallel forces? So if we are talking about the parallel forces, we are talking about group of forces that are acting in different direction but having on the same line of action. So for example, you can take two examples of this parallel force where we have the like, let's have it here as the like. We have the like parallel force, and then we have what is known as the unlike parallel force. How do this like parallel force actually appear? Like, you'll find out that this like parallel force, they have the same direction. Okay, they are acting in the same direction. For instance, let's look at this. We have a same plane here. We want to see how like parallel forces actually act. So these like parallel forces all take the same direction. I assume this is our force, the one that is having an arrow at the end. So we have this also. If we have this, that is another force. We say force is acting in a straight line. So this is another force. Maybe we can have another one right here. We can have this as our force 1. This is force 2. And then the force 3. If you look at these forces here, they are all pointing in the same direction, all upwards. Or you can also have them all pointing in the downward direction. Or you can be having them all pointing in the eastern direction or the western direction. As long as the forces are just moving in the same direction, they become like parallel forces. Why are they parallel? You can see that the forces do not intersect at any point. They all move separately. This one does not come at the point here, then they will go and intersect with this. Then as it is moving, it goes, this one will go this way to intersect with that. No. You see that they are moving in a distance. They have distance in between them. So these are the like parallel forces. What about the unlike parallel forces? So we have this as our like. Let me make it clear. We call this as our like parallel force. What about the unlike parallel force? How do they behave? Take a look at this. We have this one moving in this direction. We have this going there upwards. Maybe we have another one here down, another one there up. How is this looking like? Let's have this as our force 1. We take that as our force 2. Here force 3. And then this is our force 4. If you look at this and look at that, they don't look the same. They are totally not equal, because this force, you see, some forces are pointing upwards and others are pointing downwards. This is where they become unlike, because they do not take the same direction. All of them are moving in their own direction, apart from these two taking the same direction and the other two going their own way. So they are parallel also because they do not intersect at any point. If you take force, it is not like our force 1 is going to move there, then it comes here, as force 3 moves, comes there, then they have a point of intersection. That does not apply with parallel lines. So they are moving separately. So this is how the unlike a parallel force look like. So if we have it like that, how do you apply the principle of moments in these parallel forces? Let's take a look at this. We have, let's take a meter rule there. Then maybe we have our pivot right here. We have a force here. Let's take it as our F1. And then we have another force going there. We're taking it as our F2. Look at this situation. This meter rule cannot stand on this without, okay, if you want it to stand on this, yet you have applied a force here, that means that this one is supposed to like fall. Maybe it will just fall on this side where you've applied the force, because this side becomes heavier than this. Now here you want to balance this force here. What happens is that you've created another force upwards, going upwards to balance this other force here. Or you can even put it downwards to balance the force. So you see that this one here becomes in equilibrium. Why? Because if you see that from the principle of moments that says that the total clockwise moment should be equal to the total anti-clockwise moment for any body in equilibrium. So here our body is already at equilibrium because it is balancing each other. When you had this force, you introduce another force to balance this meter rule. So it is in equilibrium. Because of that, you're in position to apply the principle of moment in this. So what happens is that, what if this force is the same as this? What if this force here is 2? Let me say 2 newtons. You needed a force here, 2 newtons. And then this force here is equals to 2 newtons. When it is in this case, what happens? If this force here is balancing with the same, with the force here is equals to the clockwise moment, the clockwise force is equals to the anti-clockwise, that means that it is giving rise to some other thing called as known as the couple of force, or you can say it is a torque. Let me write it. So when we say that when you balance these two forces and their value is actually the same, it will give rise to what is known as the couple. We can say a couple, or you can call it a torque, which is sometimes written as, we can have it like that. That is the short form of torque. So what is this torque we are talking about? This torque, this word torque here means that we have it here as our torque, means that means that a twisting, this is a twisting force that can cause rotation. Can cause rotation. So for you to have torque, that means that you need a force, and this force here should be a twisting force. It should cause the object to rotate. Which object am I talking about? The object you are applying the force on. Let's look at this. I have my meter rule here. We assume this is our knife edge, but this time I'm going to use my hand as a fixed point. So we are placing here is our meter rule. So I want to cause rotation. I want this meter rule to rotate. What will I do if I want it to rotate? You're going to apply a force on this or on our meter rule. You can either choose to apply it this way, pulling it upwards like what I'm saying here, or you can choose to pull it downwards. But then as long as it can give it a rotation. You see this? I am pulling this. You see that what happens is that our meter rule will be rotating as you're pulling the force. So if it is rotating, because we are saying that there we have applied this, there is a twisting force on the meter rule. So for you to get this torque, that means that you need a distance also. There is a distance between the pivot and the point of application of this force. If we take this as our distance x, okay, I guess let's draw a different one. So we are going to have this. We are having our meter rule here, like this. So we have a fixed point here. Then we have a force acting this way and another force acting that way. So we are saying this is F1, and then we have our F2. This distance from this force, the point of application of the force, up to the pivot, let's call it distance x. This is our x. So what of this? Also the distance between this, to get this distance between the point of application of the force and the pivot, what if you had it here as your we're taking this as y. Now which one do we take as our distance for F2? You cannot go ahead and say that the distance of, because our point, we say that for the body to rotate, it has a fixed point. So if our fixed point is this way here, that means that this distance y is not the right distance for this force here. You've applied this force here, yes, but then what is the distance between this force and the pivot? You're taking y is from where F1 is, where you've applied F1, up to where you've applied F2. So if you want to get the distance of your F2, this force here, which is this distance right here, what you will do is you will get that the whole distance of the meter rule they've given you, and then subtract the distance of force 1 from the pivot, then you're in position to get your y2. I mean the y. So we shall have it here as your y. Our distance of this will be y minus x. Because here you have the whole of this. By subtracting y, I mean x, you're removing this distance here from this one, so it will automatically leave you with only what is from here up to here, which gives you the distance of y. So when you're getting this moment here, you'll have it as, oh, if you want to get the moment, then another thing is, in what direction is this moving? We say that it has to cause rotation with a torque. So if you pull this force, what kind of rotation is it going to give you? In what direction will your ruler be rotating? Let's have a look at, we're going to use our ruler again. This time we are taking our force F1. In what direction will that force be? Will the ruler rotate? If we are pulling this force, we are applying F1. So this one, we assume this is our F1. Now what is going to be the rotation? As you're pulling this down, I assume this is the force, I'm pulling it down. What happens to the ruler? You see, as you're pulling it down, it is moving. The other end starts moving in the anti-clockwise direction, because we say that our clock has to be moving like this way, like round. But then if it is going this way, it is already moving in the anti-clockwise direction, meaning that the direction of this force here is anti-clockwise. What of this force? What direction is it taking? Let's have a look at this again. We have this force 2 here. We are going to pull this ruler to go in the direction of this force. We are applying that force. What happens to this other end of the meter rule? We are assuming we are pulling it that way. It is still moving in the same direction, which is the anti-clockwise direction. That means that this force here and this, even though they are moving parallel, they are still having the same direction, because they are rotating in the same direction, which is the anti-clockwise direction. So to find this moment here, you'll have the moment of this force and then the moment of that force. Let's see, how shall we get the moment? So that means that to have this one, we shall have, for the anti-clockwise moment, we have this both. So this force has its distance there. We say the moment of a force is the product of the force and the perpendicular distance from the line of action. So our line of action there is going to be our fixed point, which is the pivot. So we have our anti-clockwise direction, which is, we are going to take the moment due to force 1. We shall have it as our F1, and the distance is going to be times x. We say it again, our force 2 is in the anti-clockwise direction. So we still have another force here, which is the F2. So we have our F2 times the distance between this force, application of force, and the pivot is y minus x. But then we are saying these forces are rotating in the same direction. But then you see that the arrow of this is moving upwards, and this one is pointing downwards. That means that this force here, you can subtract it with that force to see how much force you needed to balance your pivot. The meter rule, that means we shall be having here as our, we can have it as our F2 or F1, which is F1 times x minus F2x y minus x, because this is the distance. We shall look more into the example to see how we are going to apply that kind of formula in when we are trying to calculate something. So if we have it like that, what if this is with our parallel force? We say that when the forces are equal, so we shall be having what is known as the couple of the force, or which is the torque of the force. So when we are talking about this couple of the force, we said this one was the meaning, which means that the twisting force that can cause rotation. So you can also define it as it refers to two or more parallel forces whose lines of action are the same. So you see that these parallel forces should be coming from the same line or from the same plane. However much you're going to have them, as many as possible. So this application of this principle of moments, we also find it in the steering wheel of the cars. Let us see how is it that we have the steering wheel, which is taking also, you can say it is also an example of this, of the torque. So let's see steering wheel. How does it work? How do you apply this torque in the steering wheel? We all know how our steering wheel looks like. It is circular in nature. So we have it as, because I've never seen a triangle one. Maybe if any of you have ever seen that. So we have it, okay, that looks more awkward. We have it there. We assume this is our steering wheel. How does the couple or a torque help us during driving? What really happens there? You see that our steering wheel has something here. There is this distance from that part up to down, or you can take it that way. It doesn't matter. So if you take it, what happens is, what is this distance here? It becomes this is our diameter of the steering wheel of this. So what of here? What if you now take just quarter of that, okay, half of that, from here to here, or from here to here, or this one? What happens is it becomes the radius. So we have our radius 1 and our radius 2. We want to drive. So now we are driving. We are applying this force here, F1, on the steering wheel. As you're going, you have applied that force only going this direction. You're only going. How will you balance that? Or if you want to bring the car to stop, what do you have to do? You'll see that to balance your steering wheel, you will need another force which is equal to the force you first applied. But how would you apply? Will you put it in the same direction? Are you going to apply again, adding that force in the same direction like this? F2. If you apply it the same like that, what will happen? Your F1, the force you first had, you're adding another one. That means you're doubling the force there. So what will happen is that the car will fail to still balance. So you'll see that instead of applying this force in this direction, you are going to take a different direction here. So you're going to apply another force in this direction in order to balance with the first force, which is going to be our F2. So this is another torque here. So how would you find? We shall find how we are going to see how moment of a couple is calculated from such. So for now, we just want to see how would you balance your steering wheel, or how would you bring it to stop. That means you'll have to add another force here, you see, but in the opposite direction, so that it can balance with that force. That's why you see when people are driving, they go this way and then again this way. They are trying to balance the car. Because if you don't do that, you can easily slide off the road, or you can turn. So that is how the steering wheel is. We are going to see more of this calculation when we reach what is known as the moment of a couple. So for today, you should be knowing the definition of torque, or you can say a couple. So you see why a steering wheel, why people keep on rotating the steering wheel the other side, because of they are applying the torque there to balance the steering wheel. So thank you very much for attending the lesson with me today. We shall meet again in the next lesson. Bye.